Hello, my name is Lena Nguyen, and welcome to the unit on nuclear chemistry and radioactivity. Nuclear chemistry observes how atomic nuclei, which if you can recall is a small dense region of an atom consisting of positive protons and neutral neutrons, actually changes. If we compare a nuclear process to ordinary chemical processes, we realize that ordinary chemical reactions occur outside the nucleus, whether it be the making, breaking, or rearranging of bonds between atoms. The nucleus inside an atom during an ordinary chemical process remains unchanged. And because of modern nuclear science, we learned that atomic theory proposed by Greek philosopher Democritus was actually sort of wrong. The theory states that the atom is the smallest particle in existence and is indivisible. However, scientists now are capable of dividing the atom, which we will talk about in a bit. Let's first discuss radioactivity. So, radioactivity refers to the emission of radiation in the form of high energy particles and electromagnetic rays from the nucleus of an unstable atom. By emitting subatomic particles, the atom becomes more stable. So today we're going to focus on radioactive decay, the process of releasing energy in different forms of ionizing radiation, which ionizing radiation is just when these particles or rays have sufficient energy to ionize atoms or molecules by detaching electrons from them. These types of decay act to move the nucleus toward a ratio of neutrons to protons that has the least energy for a given total number of nucleons, which produces a more stable, lower energy nucleus. First up, alpha decay. Alpha decay occurs when an unstable nucleus emits an alpha particle and the number of protons in the nucleus changes and transforms into a different element. An alpha particle can be represented by helium-4 because it's composed of 2 protons and 2 neutrons. It is the biggest of all the particles emitted by radioactive nuclei and has the highest ionizing power or energy to change the chemical composition of the material it interacts with. However, it has the lowest penetrating power or the ability to penetrate matter and could easily be stopped by a sheet of paper. To describe a nuclear reaction which involves alpha decay, we can set up an equation as shown on the screen. Now let's go see an example. We first start off with our parent nuclide or original atom, which here is uranium-238. With alpha decay, we can see a resulting alpha particle, helium-4, and a resulting daughter nuclide. The daughter nuclide here is thorium-234. We can see that the element identity has changed because we have removed 2 protons. And looking at this equation, we can see that it has to be balanced and the sum of atomic numbers and the sum of the mass numbers are equal. Next up, beta decay. Beta decay occurs when in an unstable nucleus, one of the protons or neutrons is transformed into the other and emits an electron. Beta particles have less ionizing power than alpha particles, but higher penetrating power. There are 2 types of beta decay, but we see beta minus decay more often, and that's when a neutron converts into a proton. Here shown on the screen, it is an example of what a beta minus decay equation would look like. Now let's see an example. Here we have our original parent atom, radium-222. And by the way, the beta particle can simply be represented by an electron. Looking at the resulting daughter nucleus, actinium-222, radium has gained a proton and has changed its element identity. Notice how the mass number doesn't change though, as we saw in alpha decay, because the total number of protons and neutrons in the nucleus of this atom remains the same. This is the second type of beta decay, positron emission or beta plus decay. This occurs when a proton is converted to a neutron and emits a positron, an antiparticle of the electron, which just means that its mass is the same but the charge is opposite of what it normally is. So in this case, the electron would be positive. If there are too many protons, the atom will undergo positron emission for 1 less proton and 1 more neutron, helping the stability of the atom. Here we have an example of a nuclear equation. We should go see an example on how it could be different from a beta minus decay. Here we have our parent nuclide phosphorus-30 and our resulting daughter nuclide silicon-30. We notice that just like in beta minus decay, the mass number stays the same. However, the resulting daughter nuclide loses 1 proton instead of gaining 1 proton. And here we also see that the positron is represented like an electron with no mass, but has the opposite positive charge. Next up, electron capture. Electron capture is a mode of beta decay, but is usually categorized as a separate type of decay. This is where an electron in the atom's inner shell is drawn into the nucleus and combines with a proton, forming a neutron and a neutrino, which is ejected from the nucleus. A neutrino is just a neutral electron, so it has no charge. And electron capture is unique in the way that a particle is being absorbed instead of being emitted from an unstable nucleus. So our nuclear equation is going to look different from our previous ones. Now let's see an example. Here we have our parent nuclide potassium-40, and instead of emitting the beta particle or the electron, it actually combines with it and loses one proton, making a resulting daughter nuclide that is silicon-40. Our last type of radioactive decay is gamma ray emission. This is where nuclei in high energy excited states emit a gamma ray photon along with other types of radiation. Gamma rays have the lowest ionizing power but the highest penetrating power, which is why we use them in X-rays, for example. They are significantly different from alpha or beta radiation because they are a form of electromagnetic radiation and they have no mass, no charge, and is simply high energy light waves. When we look at a nuclear equation, we can see that there's no change in mass number or atomic number from the parent nuclide to the daughter nuclide. And usually we leave gamma rays out of equations because of how common it is when it's accompanied by other types of radiation. But we would include it if there was a delay between the initial delay and the subsequent emission of the gamma ray. Now let's see an example if we were to put gamma rays in an equation. Here we can see that the gamma ray doesn't do much to our equation. We have our parent nuclide uranium-238 and our resulting daughter nuclide thorium-244. This change in elements is due to the emission of an alpha particle. The only reason why we would include a gamma ray in an equation is if we needed to know about the presence of one. Here's a quick CFU over the different types of radioactive decay. Please pause the video if you would like to answer them on your own. The first question says, which type of radioactive decay emits a neutrino? We know it can't be answer choice B or C. Alpha decay emits an alpha particle and gamma ray emission emits a gamma ray photon. So we're left with electron capture or positron emission. And if we remember, positron is an antiparticle of the electron, and that means that it has an opposite charge. So if an electron has a negative charge, then a positron must have a positive charge. We look in the name of neutrino, we see neutral. So we know that it can't be D. So it's answer choice A. The second question says, what is the symbol of a particle present in positron emission? We just said that positron has a positive charge, so it can't be answer choice A or B. Let's talk about the kinetics of radioactive decay. So, chemical kinetics deals with how fast or how slow reactions occur. All radioactive nuclei decay via first-order kinetics, meaning the rate of decay is directly proportional to the number of nuclei present. So there's linear proportions. We can write an equation, rate equals Kn, where K is the rate constant and N is the radioactive nuclei. Different radioactive nuclides decay with different rate constants, meaning that if they have a larger rate constant, they will decay quickly, and if they have a smaller rate constant, they will decay slowly. Half-life is the time needed for one half of the parent nuclide to decay to the daughter nuclides. To predict the amount of radioactive material that will remain after a given amount of time, we can use half-life. Half-life is the amount of time it takes for one half of the radioactive isotope to decay. The amount that remains after one half-life is always one half of what was present prior. Nuclides that decay quickly have short half-lives and larger rate constants because they are very active and have many decay events per unit of time, while nuclides that decay slowly have long half-lives and smaller rate constants because they are less active and have fewer decay events per unit of time. Integrated rate law is just used to determine the length of time a radioactive material must be stored to decay to a safe level. Here is a quick CFU over kinetics and half-life. Please pause the video if you would like to answer on your own. The first question says, what order of kinetics does radioactive decay operate? We know that radioactive decay has linear proportions, so it must be first order. The second question says, what is the half-life of an unknown substance with a coefficient of 1 in a reaction with a rate of 7.3 times 10 to the power negative 4 seconds to the power negative 1? Give the answer in minutes. We can just substitute values into our half-life equation. So it should look like half-life equals 0.693 over 1 times 7.3 times 10 to the power negative 4 seconds to the power negative 1 and get 949 seconds. And because the question is asking for it in minutes, we will divide it by 60 seconds, which will give us 15.8 minutes. Let's talk about nuclear stability. What makes an atom stable? Well, first it must have enough binding energy to hold the nucleus together. But what binds the nucleus together? Well, strong forces causes attraction between protons and neutrons. However, strong force can only act in short-range distances. So if the number of protons were to increase, the strength of the Coulombic force, or the force of attraction or repulsion between two like or unlike charges, would increase and the nucleus would break apart. We need a balance between repulsive Coulombic forces and attractive strong forces. This is why neutrons play such an important role in stabilizing, because neutrons lack that repulsive force associated with a positive charge and keeps the nucleus together. We should note that adding more neutrons doesn't mean that the atom will have higher stability. Similar to electrons in an atom, a neutron must occupy increasingly higher energy levels. The value of stability is a plot of stable versus unstable nuclei. It's used to predict the type of radioactivity or the nature of its decay. The region of green dots are the stable nuclei, while the region of yellow dots are the unstable nuclei. To determine nuclear stability, we must use a ratio of neutrons to protons, or N to Z. For lighter elements, the NZ ratio of stable nuclei is 1, meaning there's an equal number of neutrons and protons. And for larger elements, or elements beyond atomic number 20, the NZ ratio of stable nuclei gets larger. Keep in mind that stable nuclei do not exist for elements beyond atomic number 83 because they are radioactive and involve primarily alpha and beta decay. If an NZ ratio is too high, then it means it has too many neutrons and must convert those neutrons to protons via beta decay. By undergoing beta decay, the nuclei moves down closer into the value of stability. If the NZ ratio is too low, then it means the nuclide has too many protons and must convert the protons to neutrons via positron emission or electron capture. By undergoing these, the nuclide moves up closer into the value of stability. Here's a quick CFU over the value of stability. Please pause the video if you would like to answer them on your own. The first question says, what subatomic particle plays an important role in stabilizing an atom? We know electrons and protons have some sort of charge and can't balance between the repulsive Coulombic forces and the attractive strong forces, so it must be C, neutrons. The second question says the NZ ratio of an element with a stable nucleus and 15 protons would be 1. We know that for lighter elements, or elements with an atomic number less than 20, then the NZ ratio would be 1, so this must be true. The third question says nuclides with the NZ ratio too low will move towards the value of stability via positron emission. We know that if the NZ ratio is too low, then the nuclei has to move closer up into the value of stability through positron emission, so this is true. Nuclear fusion is the process of combining two light nuclei to form a heavier one. It requires the nuclei to be positively charged to repel one another, and the process requires high temperatures. Fusion results in the emission of large amounts of energy because the resulting daughter nuclides have greater binding energies per nucleon than parent nuclides. The process is exothermic and is the basis of hydrogen bombs. And because fusion is so energy dense, people have been looking forward to it becoming a more common energy source. However, requirements to get fusion working is more difficult to achieve. Nuclear fission is the process of splitting the nucleus of an atom. It results in the tremendous release of energy. Scientists realized that it was possible to take the reaction of the splitting of one uranium nucleus and create a chain reaction or induce fission in other uranium nuclei. This is what made atomic bombs possible. It also is what made generating electricity for large communities possible, which, by the way, is a great alternative to coal burning, which generates air pollution and greenhouse gases. Products of a nuclear fission have less mass than reactants because the missing mass is converted into energy. And like nuclear fusion, this process is exothermic. Here's a quick CFU over nuclear fusion and fission. Please pause the video if you would like to answer on your own. The first question says, in blank, a chain reaction is possible. A chain reaction is when products promote or spread a reaction. So it would make more sense if the splitting of an atom and those products of that split would make more atoms split. So B, nuclear fission. The next question says, both nuclear fission and fusion release a great amount of energy. We know that both of these processes have created like nuclear bombs, hydrogen bombs, atomic bombs. So A, true. The next question says, today, nuclear power reactors are commonly using nuclear fusion. We know that nuclear fusion is difficult to achieve, so B, false. Nuclear energy can be used in so many different ways. Here's an example on how it's applied in the medical field. So nuclear imaging studies organ and tissue function and determines the cause of the medical problem. It differs from X-rays and ultrasounds, which only determines the presence of disease based on structural appearance. A radioactive substance called radionuclide or radioactive tracer is absorbed into the body. Once the body tissue has absorbed the radionuclide, radiation is emitted and detected. Healthcare providers can measure the behavior of the radionuclide during a scan and assess and diagnose various conditions such as tumors, infections, or cysts. Some examples of scans would be thyroid scans, bone scans, heart scans, or brain scans. Here are some interesting facts about nuclear energy. First being that nuclear power plants keep energy costs down. They are cheap to operate and aren't really affected by economic fluctuations that typically affect coal and gas prices. All U.S. nuclear power plants store spent nuclear fuel in quote-unquote pools. These pools are made of reinforced thick concrete with steel liners with 40 feet deep water. The fuel is usually cooled for at least 5 years before transferring into a dry cask facility for at least up to 40 years. Nuclear energy is one of the most reliable energy sources in America. Nuclear power plants require less maintenance and operate at full capacity most of the time. And that is the end of our unit on nuclear chemistry and radioactivity. Thank you so much for listening.